Alright, so hello and welcome everyone to week 13 of interactive live sessions for the course on fundamentals of convective heat transfer. The course is being offered by NPTEL, being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras, and today for the last week this session we will be solving some problems together. This week is basically a revision session in which I have tried to accumulate some problems related to each of the different topics which we covered in the duration of the whole course. So this should be a good refresher before your exam on coming 28th, I guess, or maybe dates might be different for different people. But anyway, so we will get started, and if you have any questions, please feel free to stop me and ask it then and there. All right, so without any further ado, we will get started with question number 1 of today's session, which is asking us that Newton's law of cooling, which is asking us that Newton's law of cooling states that the rate of heat transfer between a surface and a surrounding fluid is proportional to what? Is it option A, the temperature difference between the surface and the fluid, the surface area of contact, the convective heat transfer coefficient, or is it all of the above? So read the question carefully, like you have been doing so far, and pick out the correct option from the ones given below. And then once you have the correct solution, you can either unmute and answer, or you can type in the chat box as well, whichever way you feel comfortable. So this is from the fundamentals of convective heat transfer. So we already have two quick responses in favor of option D. Let's see if we get any more response on this. Yeah. So everyone seems to believe that it should be all of the above, and we will quickly have a look at the solution, and it is indeed all of the above. So the temperature difference is delta T, the surface area of contact is A, and the convective heat transfer coefficient is H. So we know that the rate of heat transfer Q dot is equal to HA delta T. This comes from Newton's law of cooling, and this is one of the fundamental equations which we use for calculating the rate of convective heat transfer. And as we have seen, all the details, all the analysis is the purpose of all that is to find out this value of H. Now this can be experimentally found out or theoretically found out. So this entire course was sort of an introduction into the theory and the analytical methods using which we can find out this value of H for different conditions. So the crux of this entire course could be said that was within finding out this value of H, the rate of convective heat transfer or the convective heat transfer coefficient, right? Any questions on this?
No, sir.
Okay, then we will quickly move along. So this is a match the following type of question in which we have two columns and four options in each column. And so what we have to do is match the following dimensionless numbers in the left column with their formulae in the right column. So I have four dimensionless groups over here and four formulae of those dimensional numbers. So what you have to do is you have to match items of column 1 to items of column 2. So the crucial thing to do here is to find out what is the formula of the corresponding dimensionless number. So there's no hurry, take your time, find out the correct answer, and you can give your answer in this way, like A1, B3, C2, D4, like this. This is just an example. You get like how to give your answer. There is no hurry. Take your time. Find out the correct solution. And once you have done so, please type in the chat box, or you can unmute and answer as well. So we already have one response telling that it should be sorry. So the very first responses say that it should be A2, B4, C1, and D3. Let's see what others have to say. Let's see if we can get any more responses. Okay, we have another one telling that it should be, sorry, once again. What is happening every time? So A1, B4, C1, and D2. So let's start solving it. We will start with the easy one. So Nusselt number. Nusselt number is HL by K. We know that it is the non-dimensional form of the coefficient of convective heat transfer. Then Prandtl number is simply nu by alpha, which is a property of a fluid and does not depend on the conditions of fluid flow. Then Grashof number is this one, which is the ratio of the buoyant force to the viscous force. So buoyant force is dependent on Bg L cube into delta T, and the viscous force depend on nu squared. And Rayleigh number is simply, so Rayleigh number is Grashof number into Prandtl number. So if we try to do this, so L cube delta T divided by nu square multiplied by Prandtl number, which is nu by alpha. So one nu would cancel out, and the numerator would be the same as that of Grashof number, only the denominator will change. It will become nu alpha. So Rayleigh number should be this one, 3. So as it turns out, the first response telling that it should be A2, then B4, C1, and D3 is the correct one. Okay, no problem, no need of being sorry. It's a simple exercise that we are doing to refresh our knowledge on this. So if we look at the solution, I have colored the matching ones in this way. So A2, B4, C1, and D3. Right? Any questions on this?
No,
Okay.
sir.
Sorry. I've stopped presenting. I'll start again. I hope the screen is visible again, right?
Yes, sir.
Yeah.
Yes, sir.
Okay. Okay. So we will, if there are no questions, we will keep moving. We'll move on to question number 3 after the session now, which is asking us which of the following is an example of a natural convection. So this is an application based question. So there are 4 different situations given here. You have to find out where natural convection is the dominant mode of heat transfer. Is it option A, cooling a hot plate with a fan? Option B, heating a room with a radiator? Option C, cooling a car radiator with air flowing through it? Or option D, boiling water in a pot on the stove? So it won't be boiling, let's say heating water in a pot on the stove. So we already have 2 quick responses, one telling that it should be C, and another one telling that it should be B. Let's see if we can get any more response. So it should be C again. Okay. Alright, so we will have a look at the solution now quickly. It's actually option D, heating water in a pot on the stove. So let's go through each example one by one. So the first one, cooling a hot plate with a fan. So I have a hot plate like this and I have a fan blowing air. So this is nothing but forced convection. In case of heating a room with a radiator, it is radiation which is the dominant mode of heat transfer. And in the third case, cooling a car radiator with air flowing through it. In this case, there is this net kind of a thing, not a net, but a series of tubes which carries the radiator fluid, and as the car moves, wind blows past it. So this is also a case of a forced convection. Now you might argue that there is no fan blowing air on it, but wind, air being stationary and the car moving is the same as a car being stationary and wind flowing through it. So and another thing is, in natural convection, the buoyant forces have to be the driving force of moving the bulk of the fluid. In this case, it's not so. It's rather the motion of the car which is the major component, major cause of bulk motion of fluid through it. So it's again a case of forced convection. And in case of heating water in a pot on the stove, so I have a pot of water like this, and let's say I am heating it from the bottom. So what happens is, this layer of fluid which is in contact with the wall which is directly being heated, that gains heat, becomes lighter than the rest of the fluid, and this rises up due to buoyant force, and colder fluid which is heavier, of course, from the top comes towards the bottom, and this sets up convection currents, and as a result this is a case of natural convection. So that's why option D should be the correct answer. Any questions on this?
No, sir.
Okay. So if there are no questions, we will keep moving. We'll keep moving on to now. This is a this will require you to solve it using a pen and a paper. So the question says that for a hydrodynamic boundary layer with cubic velocity profile, so there is a hypothetical velocity profile given here, which is cubic in nature. Find the ratio of its displacement thickness to its momentum thickness, which we also know is also known as the shape factor h, which is equal to delta divided by theta, delta star divided by theta, where delta star is the displacement thickness and theta is the momentum thickness. So what you have to do is find out both in terms of, both of these will come in terms of delta and some number. So let's say delta star would be, let's say, some C1 into delta, and theta, the momentum thickness, will also come out to be some constant into delta, let's say C2 delta. Then H should be equal to this C1 by C2, which should be a number. It could be a fraction, right? So we have seen examples like this using linear profiles, uh, quadratic profiles, and this is with a cubic profile. So only the math would be a bit involved, but the main process remains the same. So I'll give you a hint of the process as well. It's very simple though. So displacement thickness, the formula of it is 0 to delta 1 minus u by u infinity dy, and theta is 0 to delta integration u by u infinity multiplied by 1 minus u by u infinity into dy. Okay. So all you have to do is put in the value of this u by u infinity from here, and then perform the integration to find out the relevant numbers. So let's start doing it. So we have 0 to delta here, and 1 minus u infinity would be 1 minus y by delta cubed plus 3 into y by delta squared minus 3 into y by delta and dy. Now if I do this, the first one would become delta. So delta I am taking common here. Or let's say we will do this properly. So the first term becomes delta. Then the second term I have a minus here and a delta cube in the denominator. On the numerator I have 3y squared, and integration of 3y squared dy becomes y to the power 4 by 4. So this becomes y to the power 4, which, by placing delta over here would be delta to the power 4. So delta to the power 4, I have a, okay, I don't have any 3 over here, it's just simply y cube, so it's 1 by 4. And this delta cube, this cuts out to be, to give me only delta. Then the next term, so I have 3 in front and a delta square in the denominator. Y square dy multiplied is, or integrated, is y cube by 3. So this becomes delta cube by 3. 3 cancels out, delta square and this cancels out, giving me only 1 delta. Then I have minus, I have a 3 here and delta here, and y dy is nothing but y square or delta square divided by 2, right? So let's see. So if I take delta common now, all I have remaining is 1 minus 1/4 plus 1 minus 3 halves. So what does it become? So 1 plus 1 is 2. Then, okay, let's do this. So let's take 4 common here. 1 plus 1 is 2. 2 into 4 is 8. Minus 1, and minus 3 into 2 will be 6. So 8 minus 7, that is 1 by 4. So this becomes delta by 4. So delta star I have equal to delta by 4. Now let's do this one. This would be a bit more involved since it has, a multiplication of these two terms. So u by delta would be, u by u infinity would be this entire thing. I'll copy it. and this thing over here. So 3 into 4, there will be 12 terms. Handling that is a bit of a challenge. Anyway, we have to do it carefully and finally we will arrive at the answer. So let's write down the 12 terms. We'll do it one by one. Okay. So first we will multiply this term y by delta cube to all four of these. Okay. So y by delta cubed minus y by delta to the power 6 plus 3 into y by delta to the power 5 minus 3 into y by delta to the power 4. Now we will multiply this term minus 3 y by delta squared with each of them. So since it's minus, this will become minus 3 into y by delta squared, then minus minus plus 3 into y by delta. There was a cube here and there's a square here, so to the power 5 and plus, not plus, this will be minus now, and 3 into 3 gives me 9, and y by delta squared and squared becomes to the power 4, and this one becomes plus 9 y by delta to the power cube. Okay, so this is done. Now this term we will multiply with all four terms now. So this is 3y by delta. So plus 3y by delta minus 3y by delta to the power 4 plus 9y by delta squared and 1, so cubed, and again minus, wait a second, what's happening here? Yeah, so 3399. Okay, so the last one would be minus 9 y by delta squared, this entire thing dy. So I'll write the integration over here on top. So I have theta equal to, and see, look at, notice one pattern. So there is, all the terms are like this. So y to the power n divided by delta to the power n, and after integration this would become y to the power n plus 1 divided by delta to the power n, and after putting delta this will also become delta. So the order of all terms will be delta multiplied by some number. So I'll use that logic and I'll take delta common up front and just deal with the fractions now. So the first one has cube. So after integration it becomes 1 by 3. This is the first term. Now the second term has to the power 6. So it becomes minus 1 by 7. The third term has a 3 in front and 5 over here. So 3 by 6, which is half. So that's half. This is done, then this term. Now this has 4 over here. Integrating would give me 5. So minus 3 by 5. Done. This term will give me a cube. So 3 by 3 becomes 1. So minus 1. This is done. Minus 1. And this would give me plus 3 by 6, which is half. So plus half. Then this would give me minus 9 by 5. This should be plus 9 by 4. This one is y, so it will become y square by 2. So plus 3 by 2. And this one minus 3 by 5. This would be plus 9 by 4. and the last one minus 9 by 3. So minus 3. Okay. So this has to be evaluated now. Uh, I'm trying to see if there's any easy way to do this. Okay, let's at least club the terms together. So this, is there anything with 1 by 3? No. So there's only 1 by 3, 1, 1 by 7, then these terms. With the common denominator, I will club them together. So I have a plus half, plus 3 by 2. Right. So clubbing them together would give me plus 1 uh, plus 5 by 2, right? So plus 5 by 2. Then all the by 5 terms. So minus 3 by 5, minus 9 by 5, minus 3 by 5. So it is minus 15 by 5. Okay. Then I have a minus 1 and a minus 3. So it should be minus 4. Then I have a plus 9 by 4, plus 9 by 4. So that becomes 2 into 9 by 4, that is 9 by 2. And that 9 by 2 I can add to this, which will become 14 by 2. Okay. So this becomes 3, okay, and this becomes 7. So you can see that I have a 7 here and a minus 3 and a minus 4 here. So these also cancel out. So uh, all that is remaining is 1 by 3 minus 1 by 7. So this is 21, 7 by 3, 7 minus 3 into delta, which is nothing but 4 by 21 delta. So we have it now. So now the shape factor H equal to delta star by, and this is theta. So the delta star by theta, which is delta star we found out to be delta by 4, and theta we found out to be 24 by 21 into delta. So this delta delta cancels out, giving us H equal to 21 by 8. Okay, lots of math. Any questions on this? Has anyone checked the process? If there is any mistake, can anyone point out? I don't think there should be, but anyway, if you figure out something, you can tell me.
Sir, everything, no, sir. Everything is fine, sir.
Okay.
It's look, it's looking like I got lost away when I think it's okay, sir. It's
Yeah,
right,
see,
I think.
the process is
I
clear,
did
right?
like a
Otherwise,
displacement thickness, but momentum thickness I got. Yes, yes, sir. Process is clear.
okay. See, this handling these 12 terms is the main, the step where things could go wrong. Otherwise, everything else is pretty straightforward.
Yes, sir. The process is understood,
Yeah,
but the possibility there would be a mistake somewhere in the algebra.
yeah, right.
Yeah, that is the only
This is,
precaution should be taken.
yeah. So that has to be carefully done. Okay. So if there are no other questions on this, we will keep rolling. We'll move to question number 5 now, which is a conceptual question. It's asking us that the local shear stress at the wall for flow over a flat plate. So the situation is I have a flat plate like this and flow over it. So obviously boundary layer forms, as you all know by now, is given by tau w equal to some number divided
Yes.
by square root of x. So this we saw from Blasius solution also. This is the usual form that the local shear stress takes. Now, if the length of the plate is increased to 4 times its original value, so the total length of this plate, let's say this was L to begin with, and L was made 4L, 4 times its original value. Then what happens to the total friction force F? Is it option A doubled? Is it option B remains the same? Is it option C halved? Or is it option D becomes 4 times the original value? Okay, so there's a question in the chat box telling that is there any trick to solve this type of question? So I believe this is regarding the previous one. So there's no trick to it unless you find out some way to simplify the math of the integration. Otherwise, there's only one thing over there as I told. So the forms are all y by delta to the power n. So you know beforehand that after integration and putting in the value of y as in between 0 and delta, you will get delta to the power n plus 1 in the numerator and delta to the power n in the denominator. So they would cancel out to give only delta in the numerator. So beforehand you can take that out and only worry about the coefficients coming as a result of the integration. That would simplify stuff a bit. Otherwise, keep on doing every time y to the power 6, y to the power 6 by delta to the power 5, and y to the power 7 divided by delta to the power 6, y to the power 3 by delta to the power 2. No matter what you do, it would be one more in the numerator than the denominator, and you will get delta in the uh, one delta remaining. So you can take that out upfront and try to do this. Okay. So back to this question now. We have a response in the chat box telling that it should be option C, halved. Let's see if we can get any more responses. So physically speaking, do you think that if I increase the length of the plate, so I have a plate, let's say this big, and a plate this big. So this is basically what happens. So the length is increased by 4 times. Do you think the total friction force would be halved going from 1 to 2? That is, the bigger plate would have a lower total friction force. Okay, we have another 2 responses, one telling it should be A, another one telling it should be B. So pretty divided crowd over here. So let's look at what happens. So the correct answer is option A, doubled. Now, how do we go over there? So we have to first find out the total frictional force F. So if tau is some k into x to the power minus half, we have to find out the total frictional force, which is 0 to L tau omega into dx. So this is a function of x, this local shear stress. And this is friction force per unit width. Right. So if there is a width W, we will multiply W over here. But let's say for this case, let's say W equal to 1 unit width. Okay. So we will forget W for now. And we will integrate this from 0 to L. The form of this is k x to the power minus half into dx. If we plug those values in, I'll do the integration here. So x to the power minus half becomes minus half into x to the power 1 minus half, which is half. Sorry. So this becomes x to the power 1 minus half divided by 1 minus half. 1 minus half is half. This becomes 2k x to the power half. Right? And okay, so this has to be between 0 and L. So finally I get F is proportional to 2k L to the power half. Yeah. So if this L is made 4 times, F would be 2 times. So option A, double. Let's show that. So let's say my F1 was 2k L to the power half, and F2 where L becomes 4L, 2k 4L to the power half. I can take square root of this 4 outside, and I get 2 into 2k L power half, and this is nothing but F1. So F2 equal to 2 into F1. Yeah, we need to perform this integration so that we can find out the total friction force F. In the question, only the local shear stress value was given. So integrating that, you have to find out the total friction force and then see what is the functional form with respect to the length of the plate. So if L becomes 9 times, what would happen to the force?
Same doubled, sir.
No, why double? So this would be now this F2, or let's say I'll call this F3 now. So F3 would be 2 into K into 9L to the power half. So if I take square root of this 9 outside, I'll have a 3 L to the power half. This is F1, so equal to 3 F1. It would be triple.
4.5 times, I think.
4.5 times, how? There is a 9 within square root. So square root of 9 is 3, and that 3 would come out, and the rest of the stuff remaining is nothing but the original friction force that we started with, F1. Okay?
Okay, sir.
Am I? So let's say anything. Let's say if L becomes n square times L, then the F would become n times F. So if L2 is n square L1, then F2 would be n times F2. Because the functional form is this one. This F equal to some constant into L to the power half. So increasing the length of the plate would increase the frictional
I
force
did
as well.
9 by 2, sir. I did 9 by 2.
No, you
I,
can't do 9
I,
by 2. You have to take square root of 9. Right? You're getting why you need to take square root, right?
okay, sir.
Not half. 9 to the power half you have to
F1.
do.
Okay, sir.
Okay.
Yes, sir.
So the physical understanding which we should derive over here is that
Okay,
if
sir. Okay,
I
sir.
increase the length of the plate, the frictional force will also go up, but not proportionately. Like if I double it, it won't become double. If I make it 4 times, it won't become 4 times. It would only be doubled. So that increase is not as much as we expect. So if I draw a plot here of let's say L versus this friction force F, it would be somewhat like this. Starting from 0, somewhat like this. So it won't be a straight line. It would be a curve like this. Okay. Any questions on this?
Yes, sir. Yes, sir.
Okay. So let's move on. Move on to question number 6 now. This is regarding
Yes, sir.
boiling regimes like we discussed in week 12. So which of the following regimes is characterized by the highest heat transfer rate? Is it option A, natural convection, option B, nucleate boiling, option C, transition boiling, or option D, film boiling? So what is natural convection? In natural convection, we have these convection currents set up within the fluid as it's heated. In nucleate boiling, we have these droplets forming or bubbles forming and rising to the surface. In transition boiling, okay, transition boiling will come later, and in film boiling, there is a whole sheet of vapor formed above the liquid surface. And in transition boiling, we have, it's the in between stage between nucleate boiling and film boiling. So we have these discontinuous films and nucleates or bubbles rising as well. Right, so we have now two responses, one in favor of option D, film boiling, and another one in favor of option C, transition boiling. Let's see if we can get any more response. So in which case the heat transfer rate is the highest? Okay, so let's have a look at the solution. The correct answer would be option B, nucleate boiling, and that is because we will go back to this figure over here. So you see, this is A, B, C, and D. So in case of B, the uh, so okay, so the thing is, this heat transfer rate is actually a function of H into A into delta T. So in case of natural convection, the uh, delta T is the lowest. So only for 5 or 10 degrees Celsius temperature difference, we get these situations of natural convection. So over here, the heat transfer rate is not as much. In case of nucleate boiling, this delta T is higher, as well as the area is relatively high as compared to these options C and D, where the area of contact between the solid being heated, the plate at bottom, and the fluid or the liquid which is being heated is low, because there are these vapor pockets forming in between, and we know that the rate of conduction or the conductivity of vapor is much lower than that of the fluid state. So that offers a very high resistance to heat flow from the bottom plate into the fluid. So as a result, although delta T is high in these cases, the area of contact is low. So as a result, Q is also low. So this nucleate boiling is the optimal case where both A is high as well as delta is high. So this has the maximum heat transfer rate. Now if we go back to the boiling curve, we will have delta T in the x-axis and Q double dot in the y-axis. We see that it starts out small, it goes peaks over here, has a minima again, and then again increases. So this location here, something like this, is known as ONB, or the onset of nucleate boiling. So up until here is natural convection, and from here to here there is nucleate boiling, and transition also in between. then at the peak we start seeing film boiling, and after which it decreases. Right? So this point, which is known as the Leidenfrost point, where we see the observe the minimum heat transfer rate for a given T, where if I drop a sphere of liquid on a hot pan, it will immediately form a vapor layer in between, and it will keep dancing. So and not evaporate immediately. So that's a good example of this Leidenfrost effect. And after this Leidenfrost effect, again this increases due to increase in radiative heat transfer. Their convection really takes a suppressed role, and radiation dominates. And this will go up to some breaking point, where that breaking point is usually the melting point of the solid container. We can't naturally go about that. So this nucleate boiling is the case where we have maximum heat transfer rate. So am I making sense? Is everything clear?
Yes, sir.
Any questions, any comments on this? I'll go back to this slide since all of the stuff I drew is here. Any questions on this or anything related to this? Because boiling curve is a very important aspect of this
Yes, sir.
learning convective heat transfer. Yeah. Okay. All right. So we are done with question number 6. We will move on to question number 7 now, which is now asking us that for a turbulent boundary layer. Now we had 1 week where we discussed turbulence. So for this question, it's given to us that for a turbulent boundary layer, the friction factor is given by so and so. So it's given by Cfx by 2 is equal to some number k into Reynolds number to the power minus 1 by 5. And this is asking us that using Colburn analogy, find the Nusselt number Nu. And the Colburn analogy is also given, which is Stanton number multiplied by Prandtl number to the power 2/3 is equal to this friction factor Cfx by 2. And the formula of Stanton number is also given, which is the ratio of Nusselt number upon Reynolds number and Prandtl number. So Colburn analogy is an analogy which connects fluid flow to heat transfer, an analogy between the two. So all the formula that you need is given here. You just have to plug in the values and find out the expression for this Nusselt number NUX. There's no hurry, take your time, try to do this. So once you've found out the solution, you can type it in the chat box, or you can unmute and answer as well. All the formula that you need to solve this are given in the hints. You won't need anything else. You just have to
K,
plug in the values here. Yeah.
K in Reynolds to the power 4 by 5 into Prandtl number to the power 1 by 3.
Prandtl to the power 1 by 3.
G.
Okay. So this is Nusselt number is proportional to this. Let's see if we can get any more responses. So what we
Correct.
have to, yeah, please go ahead.
Nu is equal to K RE to the power of 4 by 5 and 1 by 3. Correct, sir.
Yeah, so this is correct, right? You agree with him?
The answer that person gave is correct, sir.
Okay.
Yes, sir.
Yes, sir, that is the answer. Nusselt number that is equal to constant into Rex raised to 0.5 and Prandtl number raised to 0.33. So that is raised to 4 by 5 and raised to 1 by 3.
Okay, cool. So we'll quickly try to do this. Okay, so we start from here. We will plug in the value of Stanton number. So Nu x divided by Rex into Prandtl number to the power 2/3 should be equal to Cfx by 2. Now I will plug in the value of Cfx by 2 from here, saying that it should be K into Rex to the power minus 1 by 5. Now it's a matter of rearrangement just. So NUX should be K, Rex is Rex to the power 1, so Rex becomes 1 minus 1 by 5, and Prandtl number is, if I transfer both to that side, this will become 1 minus 2 by 3. So this becomes K into Rex to the power 4 by 5 and Prandtl number to the power 1 by 3. So you see, this is a very powerful tool whereby if I only perform the hydrodynamic boundary layer analysis, so from there this formula comes, right? Without solving anything for the thermal boundary layer. And from Colburn analogy, which says that the friction factor is related to the Nusselt number in this fashion. So only using this, I can find out an expression of the Nusselt number. And we see that so without using this analogy, if we go through analysis of the thermal boundary layer also, we find out an expression similar to this. So that's the power of Colburn analogy, where you perform only the fluid mechanics analysis and you can gain some insight of the heat transfer as well. Okay, but however, there is a limitation to it. So the Prandtl number is limited between, if I can remember correctly, from 0.6 to 50 or something like that. These numbers may be incorrect, but there is a limit of validity of this expression. Okay. Any questions on this?
These numbers are correct, sir.
Okay, thanks.
Prandtl number range is correct.
Okay, thanks for confirming. Okay, any questions on this?
No, sir.
Okay, so then we will move on to last question of today's session. Now this is a refresher on numerical methods. So it's asking us to consider the second order central difference approximation for the second derivative of a function u. So u double prime, which basically means dou u, dou 2u, dou x2, is given by some u of x minus h minus 2ux plus x into plus u of x plus h divided by h squared, where h is the grid spacing. So the situation is something like this. So this grid spacing is h. I have ux over here, ux plus h over here, and ux minus h over here, And at this location, I'm trying to find out what is the value of dou 2u dou x squared. And I'm using this expression to do that. The question is, which of the following statements about the truncation error is true? So option A is the truncation error is order of h. Option B says the truncation error is order of h squared. Option C tells us this is order of h cube. And option D says that this is order h to the power 4. Which one would it be? So I guess in the class, instead of h, we had delta x, and this was given in terms of like this, order of delta x to the power n, different schemes. So in this case, if we use this scheme, what is the order of the truncation error? Is it order 1, order 2, 3, 4, or 5? We have one response telling it should be option B, that is second order. Let's see what others have to say. So the way to go about this formally is to use a Taylor series expansion. So I have ux, then ux plus h is given by u at x plus h into dou u dou x plus h squared by 2 factorial into dou 2u dou x squared plus h cubed by 3 factorial into dou 3u dou x cubed plus dot dot dot. Then u to the power x minus h is given similarly u minus h by u dou x plus h squared by 2 factorial dou 2u dou x squared minus h cubed by 3 factorial dou 3u dou x cubed plus higher order terms. Now if I do this thing, so I'm calling this equation 1, equation 2, and equation 3. Now what I'm doing is trying to represent this thing. So that should be 3 plus 1 minus, should be 3 minus 2 into equation 1 plus equation 2. Right? So doing this would give me u x minus h minus 2 ux plus u into x plus h in the left hand side, which matches this numerator, and equal to, now we will deal with same order terms. So this first term u to the power x ux cancels out. So I have 1 ux from here, 1 ux from there, and 2 ux from here. So that cancels out and gives me 0 for the first term. Then for the second term, where I have h into dou u dou x, so there I have 3 plus 2. So this and this would cancel out, right? And this cube term would also cancel out. Only this term remains. So this would become 2 into h squared divided by, now I'm writing this 2 factorial as 2 into dou 2u dou x squared. And similarly, there will be a second term, which is h to the power 4 divided by 4 factorial into dou 2u by, sorry, dou 4u by dou x to the power 4 plus dot dot dot. Now I'll send this h square to that side. So finally I'll have, so I'm dividing everything by 8 squared. So I'll get u to the power x minus h minus 2 u to the ux plus ux plus h divided by 8 squared, and this term, which was h to the power 4, will be divided by 8 squared, so this would become order 8 squared and higher order terms. So all the rest of the terms would be smaller than that. So the leading order term over here is h squared. So that's why option B should be the correct answer. Let's have a look at the solution. It is indeed option B. Okay. Any questions on this? So this brings us to the end of today's session. Thank you everyone. If you have any questions remaining regarding anything, please fire away right now.
Sir, I have a question regarding the assignment 1.
Okay.
Assignment number.
Do you want me to open assignment 1? Let's see if I'll share my screen and try to go there.
Assignment number, let me check, sir. 1 second. Assignment number 7, sir.
7. Okay. Give me a moment. I'll try to share the screen,
Okay.
then we can discuss. Yeah, my screen is visible, right? So it was in week 7, right?
Yes, sir.
Yeah, which question?
So 7th one, sir.
7th one of assignment 7.
Yes, sir.
Okay. So this is the one, right? Consider the following statements about Brinkman number.
Yes, sir.
So the first statement is if temperature rise due to dissipation is significant.
Yes, sir.
And option B is the Brinkman number is important in case where a large velocity change occurs over short distances.
Sir, actually, in the first option, if temperature rise is due to dissipation is significant, there is only condition is missing, sir. The
Yeah,
statement is
there's
true.
yeah there's a this statement seems incomplete. Okay?
Yes, sir. Sir. That's why
So
the only answer is only 2 is correct, sir.
yeah,
I'm,
there is mistake in the question. So you try
yes.
to write to the NPTEL team. I will also inform them.
Okay, sir. I do have another one, sir.
Yeah,
Let me
tell
check.
me.
Just a second, sir.
Okay.
Sir, question assignment 8, sir. 8.
Assignment 8. So, assignment 8. Yeah, which question?
Last question, sir. Last
Yes.
problem, sir.
Okay. So in a horizontal plate of area so and so, 20 watt of heat is generated. While heat is lost from it by convection as shown in the figure, the temperature of the plate when steady operating conditions are achieved is what? The Nusselt
Yes,
number for the top and bottom surface of the plate is so and so. Take the properties, calculate by taking 2 places of decimal for intermediate values, and give answer up to 2 places of decimals.
yes, sir.
Yeah, so what's your
Sir, please,
question?
can you solve that one, sir?
Okay, so let's see. I'll
Okay,
go
sir.
back to my slide again now.
Okay, sir.
Okay, so is my slide visible? Yeah.
Yes, sir.
So we have a plate like this. On top, I have one Nusselt number, let's say Nu1. On bottom, I have one Nu2. And there's a heat generation inside, which is equal to 25 watt. Right? Go back and have a look at the question once again. Yeah. 20 watt is generated. The area is 16 into 20 centimeters squared. So this is 20 watt. Sorry. The area is 16 into 20 centimeters squared. Centimeters squared. So I'll convert this to meters squared by taking 10 to the power minus 4. Okay. And what else is given? The Nusselt number for both cases, formula is given. So for the top one, it's 0.54 Ra to the power 0.25, and it's 0.27 into Ra to the power 0.25. So Nusselt number 1 is 0.54 into Rayleigh number to the power 1 by 4, which is 0.25. And the bottom one is 0.27 into Rayleigh to the power 1 by 4. Uh, okay, so then different these things. Properties are given. And the temperature difference, is it given? Yeah, someone has raised a hand. You can, if you want to say anything, you can go ahead. No issues. Is the delta T given here?
No, sir. Only like
Ah,
20 degrees,
yeah,
20.
no, it's written in the
Yes,
question, right? Assume surface temperature to be 50 degrees Celsius.
sir, yes, sir, yes, sir. Actually, Q triple dash is not given, sir. 20 watt.
Yeah, it's given, right? So in the question itself, told that
Okay,
20
sir.
watt of heat is generated,
Okay,
and
sir.
you
Okay.
have to calculate it when steady operating conditions are achieved. So things will be steady. When will it be steady? When whatever heat is generated is dissipated as well. Then
Okay,
only
sir.
it would be steady, right?
Yes, sir. Yes, sir.
So that means whatever Q triple prime is there, that should be equal to the Q double prime on both ends. So whatever heat is
Yes.
generated is uh, transferred to the fluid as well.
Okay, sir. Okay, sir. Got it, sir.
Ah,
Yes, sir. I am also having one query.
yeah, let me solve this one first. Give me a moment.
Okay, okay, sir. Sure, sure. Sorry.
So I have to find out the Rayleigh number now. The okay, my this thing is running out of charge. Give me a second.
Okay, sir.
Yeah, sorry. So let's get back here. So Rayleigh number we saw then is uh, beta L cube, what is it?
G delta.
G delta divided by nu into alpha. Right?
Yes, sir.
So Now from the different things given to us, we have to find this out. K is given, nu is given, beta and Prandtl number is given. Okay. So for alpha we need K rho Cp, and this is air, right? Okay, Prandtl number is given, so from there we can find alpha. And yeah, we do have everything. Let's see. So I'll try to put the values now one by one. Okay, so first of all, we will write this as beta L cube G delta T divided by nu square into Prandtl number, right? Because the value of Prandtl number is given to us. Now, help me out in this one. So tell me the value of each of this. Tell me the value of beta.
Beta, okay, sir. 0.00
0.00
3247, sir. Beta.
3247. This is beta.
Yes, sir. Yes, sir.
Multiplied by L cube. Now, what is L? L was given as 16 centimeter.
Yes,
So 0.16
yes, sir.
cubed into G is 9.81 into
Yes,
delta
sir.
T. Delta T is
50
how much? 20 minus
minus.
50, so 30.
Yes, sir.
What is the value of nu?
1.655 into 10 to the power of minus 5, sir.
So this whole thing squared into Prandtl
Yes.
number. What is Prandtl number?
And 7268, sir.
0.7268. Yeah. So this is the typical value for air. So if you do all this, what does the Rayleigh number become?
Let me check, sir. Just a second.
Yeah. Please calculate and let me know.
Okay, sir.
Do you want to get into the numbers or do you want me to go through the process? So once you have,
Yes, sir. Process is fine also, sir.
okay.
No problem.
So you will get some value of Rayleigh number from here. Then
Yes, sir.
you plug in those values of Rayleigh numbers here, you will get the two Nusselt numbers. Then you
Okay, sir.
put Nusselt number equal to HL by K. The value of K is also given in the question.
Okay,
And
sir.
L is 16 centimeter, as you know. So from here you will get two different H's, one for the top and one for the bottom. So H
Okay, sir.
top and H bottom.
H. Okay, sir.
And once you have got that, then this, as I said, Q triple prime should be equal to the two Q double primes. So Q double prime top and Q double prime bottom. You get the meaning of these, right? So these two are the surface heat flux from the top and from the bottom, and this is the heat generation. So
Okay,
this
sir.
we know as 20. Okay, what is the question? Everything seems to be.
Sir, the question is the temperature of the plate when steady operating condition are achieved. Is dash, sir. We have to find the temperature of the plate when it is steady, sir.
That does it make sense because it is told that
Yes, sir.
assume surface temperature to be 50 degrees
Yes, sir.
Celsius. Okay, anyway,
The-
that's for getting a estimate of the heat transfer rate. So anyway, so what you do here is you will get some H top into A into delta
delta.
T. Similarly, another thing over here, A into delta T. Now this H top plus H bottom, A, all these things you know, and
Okay, sir.
delta T would be that what T that you have to find out minus the T ambient. This is
Okay,
again that 16 degrees Celsius or something,
sir. Yes,
20 degrees Celsius. This is
okay, sir.
20 degrees Celsius, and this should be equal to 20. So all these values you know, only T you have to find out. Okay.
Okay, sir. Okay, sir. The area is pi, like L
No,
into L.
area is this thing 16 into 20. That was given in the question.
Okay, sir. Okay, sir. Okay, sir. Thank you, sir. That's it, sir.
That's
Thank you, sir.
yeah. Okay. Yes. Someone else had another query. You can go ahead now.
Yes, sir. Yes, sir. In the same assignment,
Yeah.
question number 9.
Question number 9. Let me open it. Number 9 is the one before this one. Yeah. So a 6-meter long section of a 3 centimeter horizontal hot water pipe passes through a large room whose temperature is 20 degrees Celsius. If the outer temperature of the pipe is 70 degrees Celsius, the rate of heat loss from the pipe by natural convection is how much? Yeah,
Yes.
so what's your query over here?
The properties which are given are
Hmm,
thermal conductivity, Prandtl number, and viscosity.
hmm,
Thermal conductivity, I don't think, sir, this is correct value. It should be one order less. It should be 0.02699. And I have raised this query on that platform as well,
okay.
but I couldn't get the answer. And whereas after releasing the solution for this assignment,
Hmm.
the thermal conductivity was taken as 0.02699.
Okay, so you are correct about that, right?
Yes, yes.
Uh, See, I will let them know, but this is not in my hand.
Yes,
So,
twice or thrice I have raised this query as well.
okay, okay.
Whatever the answers, those are given, so they are not matching
So I'll
with
note this down. This is assignment 8, question 9,
9.
right?
Yes, yes,
And
sir.
the previous one that you told, that was in which one? Brinkman number 1. That was in assignment 7, right? Assignment 7, question 7, if I remember correctly.
Yes, it was assignment 7 earlier one.
Assignment 7, question 7. Okay. These two things I will let them know, but it really is not in my hand. Sorry, I can't
Yes, yes,
directly
yes.
help you over here.
No
Okay.
problem.
Okay. So,
I will. Yes, sir. One. I am
yeah,
having two more questions.
yeah, please go ahead.
Yes. One question is related with the values for the Nusselt number
Hmm,
for the different types of the flows.
hmm,
Uh, we see that these values are always higher for the uniform wall heat flux condition as compared to the uniform wall temperature.
right.
So, what is the reason for this one, sir?
Okay. So, it's a very interesting question. So, I'll try to draw this thing. Yeah. So, our situation here is something like this, a boundary layer forming, and it could be either same temperature everywhere or same heat flux everywhere. So if we look at we will look at two different cases. And remember, our Q is equal to HA into delta T. I have delta T over here, or only T we will write, so that we can visualize delta T. And here, let's say the axial distance X. So this is for the isothermal case, and this is for the constant heat flux case. So if there is a constant heat flux, that means this Q double prime is equal to constant. So that would mean this delta T is also constant. So if I draw two different things, it's a T wall, and okay, let's draw this with a different. This is T wall. This is, let's say, T fluid, or even better, I'll call it T infinity. So this is how, or TF sounds better. So this is how the delta T evolves in this case, and this is constant. So that's how this heat flux is also constant. And in the isothermal case, what happens is the T wall remains constant, and the temperature of the fluid, this increases, and the rate of increase would actually depend on the difference between the two, which is decreasing. So the rate of this increase of this also reduces. So that's why this has a curve like this. So delta T is high initially, and with increasing x, this actually goes down. So as a result, this Q double dash also goes down. So in similar conditions, the isothermal case has a lower heat flux than the constant heat flux case. Does that make sense?
Yes.
It's about the temperature difference. So in a constant heat flux case, that temperature difference is maintained throughout. And in case of isothermal, after a certain distance, both temperatures come very close to each other. As a result, there is not much heat transfer between the fluid and the solid.
Yes. Yes.
Anything else?
Yes. One more question, sir. Last question.
Yeah.
Somewhere in the literature that I have studied or I have read, we know that the momentum diffusivity and thermal diffusivity are the fluid properties.
Hmm.
But
Yes.
whereas when it is to the ED diffusivity of momentum
Hmm.
and ED diffusivity of the heat,
Hmm.
they are not the properties of the fluid.
No, that is property of the flow field. So if there are, let's say, sorry. So I have a situation where there are, it's more turbulent, more eddies are formed. In that case, the eddy diffusivity of both momentum and heat flux would increase. So this alpha T and mu T would both be higher if turbulence is more. So more turbulence means what? Better mixing, more mixing. So the additional diffusivity that comes as a result of turbulence will also be higher in that case.
Okay, it depends upon the flow field, not
Flow
the flow
field. So if
property.
I have a
Fluid property.
quite laminar flow field like this versus a turbulent flow field like this where there are many eddies. So in that case, the alpha T and mu T would be higher. Even not just laminar versus turbulent, let's say more turbulent versus less turbulent. In more turbulent, the values of alpha T and mu T would be higher because there are more eddies and better mixing going on.
Okay, sir. Okay, sir.
Right.
Got it. Yes. Thank you.
Okay, so thank you so much for sticking to this entire course. It has been a great learning experience for me. I could learn a lot of things during this entire course. I hope uh, I could contribute a bit of learning to your end as well. So thank you so much,
Yes,
and
sir. Thank
we
you.
will,
Thank you, sir.
yeah,
Yes,
we'll,
definitely.
Actually,
Yes,
we did learn a lot from you also, sir. Thank you, sir. Thank you for
thank
the
you so much.
opportunity.
sir. Thank you, sir, for enrichment of the knowledge in the domain of the convective heat transfer. So
Yeah,
this would
thank you
have
so
been
much.
really helpful for all of us, sir.
Yeah. Okay,
And
thank you.
wish you all the happy Dashera.
Yeah, happy Dashera to everyone. I almost forgot.
Yes, sir.
So thanks
Thank
for
you, sir. Thank you, sir.
joining today. Happy Dashera. Bye.
Yes, sir. Bye, sir.
Thank you, sir. Good night.